Have you ever looked at the incredibly sleek, curved chassis of a modern car and then glanced at the robust, heavy-duty industrial gears inside its engine and wondered, what in the world do these two actually have in common? I mean, on the surface, they look completely different, right? But they actually share a profound, hidden manufacturing secret.
In fact, that exact same secret is probably sitting right there in your pocket. Yep, everyday coins. They're shaped by mastering the invisible, highly calculated forces of metal-plastic deformation. It's this almost magical threshold where solid metal acts, well, kind of like clay. By hitting it with intense pressure and sometimes temperature, we can mold it into literally anything, from massive structural I-beams to tiny smartphone components, all without snapping or breaking the material.
So, welcome to this explainer on the theory of metal-plastic deformation. Today, we're diving deep into the core mechanics, the math, and the dynamic real-world processes of metal forming. Whether you're an engineering student, a researcher, or just someone fascinated by how things are actually made, stick around because we're going to unlock the science behind reshaping the physical world. Here is our roadmap for today. We're covering 1. The basics of plastic deformation. 2. Stress, strain, and yielding. 3. Analysis and simulation. 4. Bulk forging and extrusion. And finally, 5. Sheet metal forming. Let's jump right in. Section 1. Basics of plastic deformation. So what actually happens to a metal matrix when it bends? To put it simply, plastic deformation is the permanent displacement of particles in a solid body under an external force. This leads to a permanent change in shape and size without fracturing. Think about a regular elastic band. You pull it, let go, and it snaps right back. That's elastic deformation. But in manufacturing, we push metal way past that elastic limit to permanently reprogram its geometry. And by tweaking variables like temperature, we can actually lower the metal's flow stress. That makes this permanent change a lot easier to achieve, while also improving the material's mechanical properties through something called work hardening. Section 2. Stress, strain, and yielding. Okay, so how do engineers know the exact moment a metal stops bouncing back and starts permanently deforming? Well, it all comes down to the yield condition. This marks the exact transition boundary from an elastic state straight into a plastic state. Imagine pulling on a cylindrical metal bar. At first it stretches, but it really wants to return to its original shape. But if the combination of stresses reaches a critical, mathematically defined value, basically a specific constant, the internal structure literally yields and plastic flow begins. The catch is, real-world manufacturing rarely involves just pulling metal in a single straight line. Forces are usually coming from all directions at once. So to map out this super complex state of principal and shear stresses, engineers use a really vital tool called Moore's circle. It's a graphical representation that takes the chaotic, invisible forces happening inside, say a block of steel, and turns them into clean, readable geometry. And this brilliantly illustrates how we translate those visual stress circles into hard math. Because you see, the yield condition has to hold true whether we're looking at simple tension or a full 3D volumetric stress state. To do that, engineers apply first-order and second-order mathematical functions directly to these circles. These equations pinpoint the exact absolute moment of yielding. So it's definitely not guesswork. It's a fundamental law of physics being translated right into mechanical engineering. All of this complex math eventually culminates in what we call a yield locus. It's essentially an intricate map that plots out different combinations of tensile and compressive stresses. Any point inside that curve, the metal is still elastic. But the very second the stress state hits that boundary line, boom, plastic flow happens. By consulting a yield locus, engineers can predict exactly how a specific alloy is going to behave under really complex loading conditions, like being pressed in a massive hydraulic die.
Section 3. Analysis and simulation.
This brings up a huge question. How do we actually calculate the massive forces required to make this deformation happen safely on a massive industrial scale? Well, we have two main approaches here. On one side, we have analytical methods. These are your traditional mechanical equations solved by hand using principles of material flow and force equilibrium to calculate the required forming force. And getting this force right is absolutely crucial for picking the right machinery and designing tools that won't just break under pressure. On the other side, we have numerical simulation, which uses advanced computer software to dynamically predict exact stress, strain, and material flow. Honestly, these numerical simulations are like a superpower. They vividly translate theory into reality. In CAE, or computer-aided engineering, when looking at models of a gear or a complex car door frame, the colors actively show you the stress and strain distributions. Before a single piece of actual metal is ever cut or pressed on the factory floor, engineers can literally watch the plastic deformation happen on a screen. They can spot exactly where the metal might get too thin, where it can wrinkle, and precisely how much energy the machine is going to need to pump out.
Section 4. Bulk forging and extrusion.
All right, now let's zoom out from the microscopic math and head to the massive factory floors. Bulk forming operations fundamentally alter the shape of heavy metal billets. We're talking about methods like open die forging, impression die forging, upsetting, and various forms of extrusion. All of these rely on immense compressive forces. Basically, you take a solid chunk of metal, which is often heated up to lower its flow stress, and you squeeze it with such catastrophic pressure that it has absolutely no choice but to flow into a totally new geometry. The actual mechanics of this follow a really structured sequence. Step 1, the billet is placed in the die. Step 2, a perfectly calculated compressive force is applied, usually by a massive hydraulic press. Step 3, the material yields and it flows. In forging, it fills the intricate cavities of an impression die. In extrusion, it gets forced through a shaped opening to create a continuous profile. And I should point out, flawless material flow here requires incredibly strict force equilibrium and absolutely perfect tool design to keep defects from ruining the whole piece.
Section 5. Sheet metal forming.
Shifting our focus from those big, solid billets to thin-walled products brings us to the highly specialized world of sheet metal. Think about the sleek casing of your washing machine or a car door. These rely super heavily on operations like bending and deep drawing. Now, bending is relatively straightforward. You're just deforming a 2D sheet around a linear axis. But deep drawing, that is much more complex. A punch literally pushes a flat metal blink down into a die while it's secured by a blink holder, forcing that 2D sheet to seamlessly transform into a 3D cup or a really complex hollow shape. As you can probably guess, controlling the geometric changes during these operations is a super delicate balancing act. In deep drawing, the metal at the edges of the flat sheet has to travel all the way down into the die. If it moves too fast, the metal wrinkles up. If the punch pushes too hard, the metal stretches and just tears apart. So whether you're performing deep drawing, bending, punching, or nosing, controlling this deformation requires some ridiculously precise calculation of the punch force and the blank holder force. That's the only way to ensure the transition happens smoothly across the entire part. So, we've journeyed all the way from the fundamental, microscopic equations of plastic yielding, right up to the massive industrial presses that shape our world. But here's a quick thought to leave you with. As material science rapidly evolves, and we keep developing these ultra-strong, incredibly lightweight alloys for things like deep space exploration and advanced aerospace, are these traditional laws of plastic deformation going to hold up? Or will the engineers of tomorrow need to completely rewrite the yield locus to shape the future? It's pretty wild to think about. Thank you so much for joining me for this explainer, and as always, stay curious.